Today I'm going to talk about a much simpler way of determining planetary orbits in classical mechanics, and also I'm going to talk about a very surprising connection between classical and quantum mechanics. So the conventional way to determine Kepler orbits is quite complicated, and I'm going to summarize how Goldstein does this in his textbook. So you start from the equations of motion. I'm going to get a little pointer here. R dot is PR over M. PR dot is the force, which is L squared over MR cubed. That's the centrifugal force. And then the Coulomb inverse square force minus, gravitational inverse square force, K over R squared. And then the angular equation of motion is theta dot is L over MR squared. And of course, L dot equals 0 because it's a central force, so there are no torques on the system. You can then take this equation, take its time derivative. That'll bring in a PR dot, which you can replace by the force. So you get R double dot is equal to this expression here. Now, the standard thing you do in classical mechanics is you multiply by R dot. Recognize then that R dot times R is the time derivative of 1/2 R dot squared. So you can integrate that. And if I integrate this with respect to R, I will get a constant, which we call E. And then I get these two terms, and these are essentially the potential energy or effective potential energy, including the centrifugal term. So this is, in essence, an equation that's looking at energy conservation, where the total energy is kinetic plus potential. Okay, but we're not working with the energy itself. We're going to now solve for R dot and replace the R dot by a dr d theta. So to do that, we have to recognize that this equation up here can be written as mr squared over L d theta equals dt. And then solving for R dot here, R dot is the square root of this mess. You can write that as dr d theta times L over mr squared. You can then take the L over mr squared, move it to the other side. Actually, we're going to take the square root, move it to this side, and the d theta, move it to the other side. And what you end up with is this equation. D theta is dr times what is now a function of r. And while it looks like this is a mess, this is actually something that can be integrated. So we then go ahead and integrate it. On the left-hand side, that will just become theta minus the initial angle. On the right-hand side, as I said, you got to go look up in an integral table, but it is minus the arc cosine of this mess. You then take the cosine of both sides and do some rearranging, and you find 1 over r is equal to mk over L squared, 1 plus this constant times the cosine of theta minus theta naught. And this kind of expression, 1 over r is a plus b times cosine. That is the equation of an ellipse with the origin placed at one of the foci of the ellipse. And I just want to impress upon you that this is a pretty complicated way of deriving the orbit. You first have to go through all those equations of motion. You have to essentially do two integrals. You have to do one integral to get the energy. You then have to convert from functions of time to functions of angle. You then have to integrate again. Then you have to take cosines of both sides and so forth. So it's a quite involved derivation. Okay, so the idea for the simplification actually comes from a very unlikely source. In 1930, Born and Jordan wrote a quantum mechanics textbook called Elementary Quantum Mechanics. It is not a very well-known textbook. It was written primarily to promote matrix mechanics, which was already essentially dead by 1930. But in the textbook, they have this very interesting comment, and I hope that you can see it. Here they're looking at the harmonic oscillator, where they have Q dot is P over the mass. P dot is equal to minus a constant times position. And they introduce these two quantities, which are linear combinations of momentum and position, such that, unfortunately, this is hiding it a little bit, such that B dot is a number times B. And that has then decoupled these two coupled first-order differential equations. Now, this is a standard technique in mathematics when you have coupled first-order differential equations. You can decouple them by finding the right linear combinations. And we're going to do that now. We're going to use that approach for the Kepler problem. So we start with the same equations of motion. R dot is PR over M. PR dot is the force, and theta dot is the angular momentum, and the time derivative of the angular momentum is equal to 0. But now what we do is we want to find a quantity that's a combination of these objects. We want to choose alpha and beta so that these first order differential equations become decoupled. So to do that, we just take the time derivative. That gives us a PR dot. It gives us minus alpha r squared r dot. Time derivative of beta is 0. And plugging in for PR dot using the equation of motion gives us these two terms. And we replace the r dot by the PR. Now, if this is going to be a number times a, this coefficient of PR is the thing that we have to factor out. So we're going to factor that out. And when we factor that out, you see we get something that is in the required form, alpha over r plus beta. You see here? So now all we have to do is extract the alphas and the betas. And so the equation for the alpha is simply alpha is equal to minus L squared over alpha, which can be solved by alpha is plus or minus IL. Then the beta becomes minus plus I mk over L. And the number that, or the coefficient that we get for decoupling this equation is minus plus IL over mr squared. Now, using the fact that L is equal to mr squared theta dot allows us to replace this by theta dot. Now, if you look at this, this is an incredibly simple equation. A dot is minus plus I theta dot A. It can be immediately integrated. The solution is A of theta is A0 e to the I theta. A star of theta is A0 star e to the minus I theta, where A of theta is just PR plus IL over R minus IMK over L. You can think of the theta as just the angle, or you can think of the theta as some theta of t if we knew exactly what the theta of t dependence was. But you can see it's an incredibly simple solution. Now to get the orbit, I just want to get rid of this PR term. So we're going to show you how we do that. So we first need to determine the constants for A0, and to do that, we pick the point of closest approach where PR is equal to 0, and then A0 is just equal to L over R0 minus MK over L times I. And then we get rid of the PR by taking the difference of these two objects. IL over R minus IMK over L is just 1/2 the difference of these two terms. And using these expressions with this A0, we can rewrite that as IL over R0 minus MK over L cosine theta minus theta 0. And you see we now have the equation for the orbit. And the only thing that we had to integrate was an exponential equation. Super easy. We didn't have to take cosines of either sides or anything like that. All follows very, very simply. So,
Sorry, Jim.
mhm.
What was the assumption for making PR equal to 0? Probably you'd mentioned it, but I missed it.
At the point of closest approach, PR is 0. It's not moving in or out radially. It just has
Yeah,
angular
okay. So
motion.
there is no movement. Okay.
No, this is just the result of an orbit. At the extrema, you can think of the orbital motion as separated into angular motion and
Yeah, yeah,
radial
yeah.
motion. The angular motion is conserved because the angular momentum is conserved, and the radial motion oscillates back and forth between a minimum and a maximum value of r. And at the turning points, there's no radial momentum because
True.
that's where it's turning around. The momentum is now changing sign, so it's equal to 0 at the extremum. So the PR is 0 at the point of closest approach. It's also 0 at the point of farthest approach as well. Okay.
Yeah, so okay, then why you're considering the closest approach or not?
We have to determine A0. So the easiest was, so R0 is the point of closest approach. You could determine
Ah,
it at some other
gotcha.
angle, and then R would be whatever the R is, but then you have to say what the
Yeah,
PR is, which of
yeah,
course
gotcha.
makes it more complicated. It's much easier, it's easiest to express the integration constants at the distance of closest or farthest approach.
Gotcha.
Okay? All right, so in my opinion, using this approach of decoupling the differential equations is a much simpler derivation than the standard one, and it doesn't require any complicated integration that you have to look up or get Wolfram alpha to integrate for you and so forth. But there's more that you get from this. So let's take a look at energy. The energy is PR squared over 2m plus L squared over 2m R squared minus K over R. If I add this constant, that is actually what 1 over 2m A star times A is. So the energy is related to A star times A. This is equal A star times A because the e to the I theta and e to the minus I theta will cancel is just 1 over 2m, which is A0 squared, which is a constant. So if I move this constant to the other side, you can see that it's going to tell me that my total energy is conserved. So you automatically get energy conservation in one line using this approach. And then here's the thing that's real, I think is really particularly cool. I'm going to just summarize again what A is and what A star is. If we now make them operators and we use the canonical commutation relation between the radial coordinate and the radial momentum, which is the commutator between R and PR is IH bar, then if we calculate 1 over 2m A dagger A, which we know should be related to the energy, we just plug in what the two results are, we multiply them out, keeping in mind the fact that the order matters. So we actually pick up a commutator from the cross terms because this has a positive sign, but this term has a negative sign. You find you get PR squared over 2m, you get the commutator from the cross terms, and then you get the square of these two terms, which gives you L squared over 2m R squared minus K over R plus MK squared over 2L squared. You can evaluate this commutator. It is equal to IH bar 1 over R hat squared. And so that can then be combined with this term into L squared plus H bar L. And this is the quantum mechanical Hamiltonian plus a constant. And I think that should actually be minus EL. This is minus EL. That's a typo. I'm sorry. I'll get that fixed. Where EL is this actually will be the energy of the quantum mechanical state, because whenever I can write a Hamiltonian in the form of A dagger A plus a constant, the constant is the ground state energy. So this actually becomes the solution for the hydrogen atom if we let the angular momentum equal H bar times L, an integer L. So the simplified treatment of the classical orbit also provides a very neat connection to the quantum mechanical solution. So I think this is really cool. Even though Born and Jordan didn't actually figure this part out, it is inspired by the work that they did. And Leanne and Jason have been involved in this work, and we're funded by the Air Force Office of Scientific Research, and I also get funding from the McDevitt bequest at Georgetown. So that's all for this particular talk. I can say, I'm going to stop sharing. I can say that one of the interesting things about this that we've been looking at is you can actually generalize this to solve any quantum mechanics problem. And if you want to think of this as a way of providing a classical quantum correspondence, when you look at the harmonic oscillator, this way of doing it leads directly to the equation of motion for coherent states for the harmonic oscillator, which we know the expectation value of a coherent state gives exactly the classical equation of motion with the freedom to choose an initial position and an initial momentum. We believe by working in this way and looking at a classical quantum correspondence as opposed to the Airinfest theorem, what you find is you have a different Hamiltonian or a different potential for the classical problem than you have for the quantum problem. And what it is that's going to be the same is the equation of motion expressed in terms of the A object. So in classical mechanics, it's just a combination of momentum plus a function of position that decouples the differential equations, while in quantum mechanics, it's an operator equation. But the form of the equation of motion is identical between classical and quantum mechanics when you have slightly different potentials. So one is a classical potential, one is a quantum potential. In fact, the equation of motion is determined by the difference between the quantum potential and the classical potential, which is an interesting result as well. We're trying to work out the details of exactly what this correspondence means, but I find it, quite interesting. It's a way of sort of generalizing coherent states beyond what is done in classical mechanics, but in a way that is, as far as I can tell, quite different from the way anyone else has done it before. Um, so, so if you guys have any questions or comments, certainly happy to hear them. Either it was incredibly clear or it went right past everyone.
Can you elaborate more? I was confused when you said as opposed to the Airinfest theorem. What does that mean?
So the Airinfest theorem says that for any quantum state, it's actually very confusing the way the Airinfest theorem works. What it says is for any quantum state, if you take the expectation value of x dot and you take the expectation value of p dot, those expectation values are the same equations in quantum mechanics as they are in classical mechanics. So, x dot is just the expectation value of x dot is just the expectation value of p over m. That holds exactly in both classical and quantum mechanics. Expectation value of p dot, the way we do that in quantum mechanics is we would calculate the commutator of h with p, but the commutator of h with p does give us the derivative of the potential. And so it becomes the expectation value of the derivative of the potential, and that would be the force. And that's the way the classical equation of motion works. So it looks like if you have the same potential in classical and quantum mechanics, you get these equations of motion that are exactly the same. What it doesn't say is in many cases, when you take that expectation value in quantum mechanics, you don't have the full freedom to adjust the initial position and the initial momentum. So as an example, take a harmonic oscillator. If you take the expectation values in any energy eigenstate, because the expectation value of P involves a minus A dagger, if I put that in two energy eigenstates, it's just zero. And if I do the same thing with the force, which is proportional to X, I also get zero. So all the Airinfest theorem says is 0 equals 0 for energy eigenstates of the harmonic oscillator. Not particularly interesting. Okay. But one of the things that is interesting is that when you take the expectation value of the force, that is not, the derivative of V of the expectation value of X. If it was that, except for harmonic oscillator, that's the one case, because in harmonic oscillator, the force is linear in X. If it was equal to V of the expectation value, then it would have exactly the same form as the classical equation of motion. What we're saying is something different. What we're saying is there's a separate classical and quantum potential. They're different. And we won't get the Airinfest equations of motion, but instead what we will get is the equation of motion for this A object has the same form. And if I take an expectation value of that, that will have the exact same form as the equation of motion for the classical problem. But of course, the things that are inside the expectation value are operators in the quantum case. So when you actually evaluate it, you will again get something that is different. But by working with what we're going to be working with is a ground state that is displaced. So you can move it to any position and you can give it any momentum. And that then allows you to have all possible initial values of position and momentum. And that is that then leads to what I think are, an interesting new way of thinking of doing a classical and quantum correspondence. And you can actually construct everything just starting from a function that's square integrable and has no nodes. That defines the potential, the quantum potential, and it then determines the classical potential, and it determines the equations of motion, and everything follows just by starting from any function you want, and you can find an interesting classical quantum correspondence. So it's a somewhat different way of looking at this connection between classical mechanics and quantum mechanics.
I have a question, which is
Mm-hmm.
in the other direction. So, I mean, you use this trick from quantum mechanics to go to the classical one, but
Right.
is there any equivalence, like for the planetary motions, you have this Kepler laws, the three Kepler's
Right.
law about like the area of the is proportional to, I don't know, the time. So is there any equivalence of that in quantum mechanics where
Yeah, I mean, that's an interesting question. I don't think there is for things like area laws because the
there is
objects don't
no,
go on orbits.
but
There is a conserved Runge lens vector. So, in the Kepler problem, angular momentum is conserved and energy is conserved. That's true for every central force problem. But actually, the energy is just one component of a vector called the Runge lens vector that's actually also conserved. It's a vector that points from the focus of the orbit to the point of nearest approach, I think. And so there are actually three more conserved quantities, and I think those are related to Kepler's laws, although not, I think you have to work at it to figure out the relationship. But this is the way that Pauli solved hydrogen before there were wave equations. He worked with the fact that the Runge lens vector, he first showed that the Runge lens vector is conserved. And then because of that, he could generate an algebra that allowed him to find the spectrum of hydrogen. It's actually a technique that we don't really use for solving quantum mechanical problems. The method is that you find all conserved quantities of your quantum problem, and they typically become a Lie algebra. And by looking at the structure of the Lie algebra and the representations of the Lie algebra, you can get all of the energies of the system. So I believe every exactly solvable problem can be solved with this Lie algebra way of doing things. And I even have a book that kind of shows how it can be done. I've never had the time to spend to go through it in detail to understand all of the ins and outs of how that works. But when you have that kind of underlying Lie algebra structure, it also allows you to get a lot of information about different kinds of matrix elements as well. I think there are deep connections that are not super obvious. Did you find this surprising? Most of you probably don't remember the torture you went through in finding Kepler orbits when you were in college. I remember it as not being very pleasant.
I blocked out that part of classical mechanics.
Yeah, because you got to play with that integral a bit to get into a form where you can just say what the integral is.